Hi students, welcoming all for the online session. I am Madhavrao Alla, working as assistant professor in the Department of Electronics and Communication Engineering, Vignans Lara. Okay, in the previous class, we discussed about what is signal, what is system, and examples for signals and examples for systems. And I finished that session with continuous time signals and discrete time signals. And in the last class I told you that in the next class I will start with the classification of signals. So today's topic is classification of signals. How the signals are classified. That is today's topic. So I will start the today's topic with classification of signals. Okay, how the signals are classified. First, basically, the signals are classified into two types. All of you know, I already told you, the two types are, first one is continuous time signal and the next one is discrete time signal. Basically, the signals are classified into two types, continuous time signal and discrete time signal. Okay. Again, these continuous time signals and discrete time signals are classified into many ways. What are they are? First one is a deterministic and non-deterministic signals. A deterministic and non-deterministic signals. Next, periodic and aperiodic signals. Periodic and aperiodic signals. Even and odd signals. Even signal and odd signal. Energy and power signals. Energy and power signals. Causal and non-causal signals. Causal and non-causal signals. There are so many ways these signals are classified. So some other ways are real and imaginary signals. Another classification is real and imaginary. So I am explaining one by one after the other. Okay. First one I will start with the continuous time signal and discrete time signal. So basically the signals are classified into continuous time signal and discrete time signal. Okay, these continuous time signals and discrete time signals are again classified into deterministic and non-deterministic signals. Okay, next one, periodic and aperiodic signals, and next one, even and odd signals. Even and odd signals, and next one, energy and power signals, causal and non-causal signals, real and imaginary signals. So there are so many classifications. Okay, so the main classifications I am explaining here. Okay, now we will start with the continuous time signal and discrete time signal. I hope you will all learn this in the previous class itself. I am once again repeating it and giving more examples, graphical representations for this continuous and discrete time signals for your better understanding. Generally, these continuous time signals are nothing but analog signals. In nature, most of the signals are analog in nature. That is, most of the signals are continuous signals. Okay, so we can convert these continuous signals into discrete signals by a process called sampling. It will come in the later sessions. Okay, so simple continuous signals can be converted into discrete signals, or you can directly get the discrete signals itself. Okay, so first one, most of the signals are continuous time signals. Continuous time signals are nothing but analog signals. Okay, and discrete time signals which are having finite values are called as digital signals. The discrete time signals which are having finite values are nothing but digital signals. Okay, so first I will start with continuous time signal and discrete time signal. Let us see. Continuous time signal. Okay, so what is the definition for continuous time signals? Which signals are called as continuous time signal? The name itself tells it is a continuous. Here the signal is varying continuously. So simple definition is the signals that are defined for each and every instant of time are nothing but continuous time signals. The signals that are defined for each and every instant of time are nothing but continuous time signals. Okay, so here at any instant of time I will get the value of that function. At any instant of time I have to get the value of that function. Then that signal is called as continuous time signal, and the continuous time signal is represented with x of t, and the continuous time signal is represented with x of t. Okay, this one, the continuous time signal is represented with x of t. Now, so here these signals are defined for each and every instant of time. So at every time instant I will have a value for that function. Okay, I have a value for that function. Then only we can call that signals as continuous time signals. Let us take this example. Okay, so here the wave is continuous. As on seeing the wave we can say that the wave is continuous. Okay, first thing. Now let's this point, wave is continuous. Okay, 0, this point, this point, this point, this point, this point, this point, and anywhere. So at this time instance it has some value. At this time instant it has 0. At this time it has some value. There has some value. At this point it has. So at every time instant it has some value. At every time instant it has some value. It is showing some value. There is 1. This may be 0.5. This may be 0.3. This may be minus 0.2, minus 0.5. So at each and every time instant we have the value for the function x of t. Hence it is called as continuous time signal. So as it is varying continuously, there is no gaps for that signal, and at every instant of time I am getting the output signal, output value. Hence it is called as continuous time signal. Okay, clear? So this is the continuous time signal. Now same example, another example, continuous time signal, a sine wave, same examples. Okay, na? So we can consider this at this value. At this point we have some value. At this point we have some value. At this point we have some value. At this point we have value. At this point we have some value. At this point it is some value. At each and every time instant it has some values. So for that reason these signals are called as continuous time signals. Let's take here on x-axis I am taking the time. On y-axis I am considering the amplitude. Let us consider the signal as x of t, where t is the independent variable which represents the time. So I am taking time on the x-axis, where the time is the independent variable. Now the function is x of t, so that we represent that some amplitude that is on y-axis. So the x of t is dependent. So dependent on the independent variable t. So the function is dependent on the independent variable t. The t values changes, automatically the x of t also changes, because for different values of t we have different values of x of t as shown in the graph. Okay, since as t is continuous and the amplitude is also continuous, so in this continuous time signal both time and amplitude are continuous. Both time and amplitude are continuous. So in this continuous time signals, time on x-axis is continuous one, as well as amplitude is also continuously varying. So both the time and amplitudes are continuous in continuous time signals. Okay, so this is a brief introduction about continuous time signals. So most of the signals are continuous signals only. So in general we call it as analog signals. Okay, analog signals. Now next, discrete time signals. Now the discrete time signals are defined at discrete instants of time. the signals that are defined at discrete instants of time are nothing but discrete time signals. Discrete time signals. So here the x-axis will take the n, the value of n, and the function will represent as x of n. Hence the discrete time signals are denoted by x of n, where n is an integer 0, 1, 2, 3, or you can go for -1, -2, -3 also. Okay, so these are the values of n. Here the discrete time signal are denoted by x of n. The discrete time signals are denoted by x of n. Yeah, the discrete time signals are denoted by x of n. Very, very important. So whereas continuous time signals are denoted by x of t, here the discrete time signals are denoted by x of n. First one. And these discrete time signals are defined at discrete instants of time. That is, here the time is not a continuous one. The time is not a continuous one. Here the time is variable in discrete points. So discrete point, let's take this one. Discrete. So this is time instant. This is time instant, time instant, time instant, time instant. Let us take this as 0, 1, 2, 3, 4, 5, 6, -1, -2, -3. Okay. So at 0 I have some amplitude x of n. At 1 I have some amplitude. But what about 0.5? There is no signal at 0.5, and there is no signal at 1.5, and there is no signal at 2.5, 2.3, 2.9, whatever it may be. So this time is not continuous. It is discrete. 1, 2, 3, 4, 5, 6. That's one. There is no value of 1.9 or 2.7 or 8.2 or 5.3. There is no such type of values. Hence, it is nothing but time is discrete. Hence, it is represented with n. It is represented with n. Okay, and these functions will consider as x of n. X of n. So here the signals that are defined at discrete instants of time, are nothing but discrete time signals. So the discrete instants are 1, 2, 3, 4, like integers. So I will consider that as n. So the function is represented with x of n. This is also example. This is also another example. Here we have to take the small samples. There we take the larger samples. That's both are same. So in the previous slide, we have two sinusoidal signals. So these two sinusoidal signals are sampled. So on sampling this sinusoidal signal, we can get the discrete signal. So it's very simple. So how can we get a discrete signal from a continuous time signal? It's very, very simple. Let us see. This is a continuous signal. Okay. If this signal is multiplied with a unit time pulse, simple. Okay. Now at this instant, see, this one, whatever the value at this will be appeared at the output. Simple. At this instant, value at the output. At this instant, the value at the output. At this instant, value at the output. At this. So here this signal will be multiplied with this signal. See, at this point, let's see, at this point the signal is this one. So 1, let's take 0. 1 into 0, 0. Next 1 into, let us take, this is 2. 1 into 2, 2 it gives. Let us take again 1 into 3, 3. 1 into -2, -2. 1 into -1, -1. 1 into 4, 4. So whatever the value that is present at this point, that will be there. Okay. So this is just converting a continuous time signal into discrete time signal. Okay, we will get this in clear in the coming sections or the coming units. Okay, for your understanding, I go on through a simple example. So this continuous time signal will be converted into a discrete time signal just by multiplying with a unit pulse, unit discrete signal. Okay, unit time pulse. Now, so this is regarding the discrete time signals. Now coming to this one, these signals are continuous in amplitude, they are discrete in time. Already explained many times. So in time it is not continuous, it is discrete. So it is discrete in time, whereas it is continuous. The amplitudes, we have the continuous amplitudes. Whatever the amplitude, we have the continuous amplitudes. Let us take continuous amplitudes. Continuous amplitudes. We have continuous amplitudes. Okay. So these signals are continuous in amplitude but discrete in time. Whereas continuous time signals are continuous in both time as well as amplitude. So this is the main classification regarding the continuous time signals and discrete time signals. Continuous time signals and discrete time signals. I hope you will surely get what is a continuous time signal and what is a discrete time signal. So if anyone asks what is a continuous time signal, the signal that is defined at each and every instant of time is nothing but a continuous time signal. It is denoted by x of t. What is discrete time signal? The signals that are defined at only discrete instants of time, those signals are called as discrete time signals, and they are denoted by x of n. Continuous time signals are denoted by x of t. Here the discrete time signals are denoted by x of n, where n is an integer. Okay, 0, 1, 2, 3, so many values like I explained before. Now the continuous time signals are, in continuous time signals both the time and amplitude are continuous, whereas in discrete time signals only the time is discrete and amplitude is continuous. Only the amplitude is continuous and time is discrete in discrete time signals. Next, graphical representation of some continuous time signals and discrete time signals. Now I am explaining the graphical representations for some continuous time signals and discrete time signals. So I already explained you how we can get the discrete signal from an continuous time signal. Let's say this is a continuous time signal, continuous because it is continuously varying with respect to time. It's continuously varying with respect to time. Let's take this is t, and we consider this as x of t. X of t. Okay, so this is continuously varying. Now if we multiply this signal with an unit impulse train, then automatically we get the samples at that unit impulse train. So if the samples are larger, we will also get larger ones. If the samples are smaller, samples we will get small samples. So the time between the time, in the distance between the two successive signals in the time axis will be reduced. Simple one. So this one. So for this it will be the discrete version. So this is a continuous time signal and this is the discrete time signal. Now we have to remember that. So here the discrete time signal on x-axis we will consider as n, and on y-axis we have to consider as x of n. So that is in continuous t it is x of t, in discrete it is n and x of n. Next one. So we will move next to graphical representation of continuous and time discrete signals. Another example. I had gone for 3 examples. Okay, the first example, the second example. So continuous signal, amplitude on the x-axis, time on the y-axis. So we had taken a continuous time signal. So this should be converted into discrete like this. See, if you join all this top of the pulses, if you join all this top of the pulses, what will you get? If you join all this top of the pulses, see, the signal is same as the continuous time signal almost. So this continuous signal can be converted to discrete time signal by multiplying with a unit impulse time. Simple logic. So I will clearly and fully explain this in the coming sections. So now here what you have to know, you have to understand what is a continuous time signal and what is a discrete time signal. So here always we don't convert the continuous time signals into discrete time signals. In some cases we have the direct discrete signals. We have the direct discrete signals. Okay. Next one. A graphical representation of the continuous and discrete time signal. The last example is a clear example. So this signal represents a sine wave. This signal is a sine wave. So the discrete versions of sine wave. Discrete versions of sine waves. See, this is the seventh second. At 7 second, what is the value? 0, and we consider this as a 10. At 7th, what is the value? So the same value will be displayed here. So here the sampling time is very small. The reduced small samples they are taken. Small sample, the distance sampling time will be reduced. Hence we get as the sampling time is reduced, we will get a perfect shape of the continuous time signals. Okay. So here the main important thing what you have to remember is what is a continuous time signal and what is a discrete time signal, and how the continuous time signals are represented and how the discrete time signals are represented. Okay. So what about the time and amplitude of variations in continuous, and what about the time and amplitude variations in discrete? So this is what you have to know. Now, how a discrete signal, continuous time signals are represented with a functional way. Okay, no? We can go for a function, can represent it by a function. Here, the discrete time signals can be represented in the form of a sequential manner. So we can represent a discrete time signal like this. You all know how a continuous time signal will be represented. In generally, almost right from the start, we learned about the continuous time signal. So we all know about the representation of a continuous time signal. Now, how a discrete time signal will be represented? Actually, there are 4 ways to represent a discrete time signal: graphical way, graphical approach, or tabular approach, or we can go for sequential. Okay, we can go for sequential or functional way. We can go for the functional way. So sequential way, generally it will represent with the sequential way. So here we will represent x of n is a set of values 1, 5, 7, 8. Okay, this is what they had given. So we have to know x of, I said n equal to 0, 1, 2, 3 and so on. So where I have to start? Which one is x of 0, or which one is x of 2, or which one is x of 5, or which one is x of minus 5? So for that they have to give an arrow mark below the number where it starts with 0. If they are given the arrow mark, that represents the signal is starting at 0 of that value. That value is for x of 0. That value is for x of 0. So if they represent like this, so this means for this signal, x of 0 equal to 5, x of 1 equal to 7, x of 2 equal to 8. Then this is 0, 1, 2 and this one is minus 1. So x of minus 1 equal to 1. So is what they have. So x of minus 1 equal to 1, x of 0 equal to 5, x of 1 equal to 7 and x of 2 equal to 8. So this we get all this by this arrow mark. Okay, if it doesn't mention that arrow mark, we consider the first one is the x of 0. First one is x of 0. First element of the set is x of 0. In general, they will specify the arrow mark because they have to mention the x of 0 value. Then only we get the correct representation of that discrete time signal. So in this way, a discrete time signal can be represented. So this is regarding the continuous time signals and discrete time signals. Okay. So x of n values, we have n number of values, 10 values also. They will give at one number, below that number, they will give an arrow mark upwards. So like this. That means that is the value of x of 0. From that, move front side, x of 1, x of 2, back, x of minus 1, x of minus 2 and so on. Okay. So this is a simple representation of an discrete time signal. Okay. Next, coming to the next ones. Now these continuous time signals and discrete time signals. These continuous time signals and discrete time signals are again classified into so many ways. I already told you. What are they? They are deterministic and non-deterministic signals. So a continuous time signal may be treated as deterministic or non-deterministic. In the same way, discrete time signal may be deterministic or non-deterministic signals. Okay, or periodic and aperiodic, even, odd, energy and power signals, causal and non-causal signals, real and imaginary signals. There are lots of signals classifications. Okay, now coming to this one, deterministic and non-deterministic signals, deterministic and non-deterministic signals. So I will give the examples for both continuous time signals as well as discrete time signals. That comes on the latter part. So first off, we have to see what is a deterministic signal. What is a deterministic signal? So deterministic, the name itself tells we can determine the next instant of the signal. So we can determine the signal in the coming instants. So what the next instant of the signal we can determine, then we can say that that is a deterministic signal. So we cannot predict the next instant of the signal, then that signal is not considered as non-deterministic. So we are unable to determine what the next instant is. Here simply for practical definition, a signal exhibiting no uncertainty with respect to its value at any instant of time. Simple. A signal exhibiting no uncertainty. There is no uncertainty. We know what the next instant of signal is. Then that type of signals are called as deterministic signals. I am once again repeating. A signal exhibiting no uncertainty with respect to its value at any time instant of time. A signal exhibiting no uncertainty with respect to its value at any instant of time or any time instant. At any time instant. Those signals are called as deterministic signals. Okay. Now, these deterministic signals, we can know the next instance. So simply we can represent those signals by using a mathematical equation. We can represent those signals by a mathematical equation. They are denoted, they are represented. Okay, they are described by the mathematical equation. Okay, so general example for a deterministic signal. We can take sine function, sine omega t. Sine omega t is an deterministic signal. So we know the sine function or cos omega t. I know the cos function also. So the sine functions and cos functions are the examples for these deterministic signals. So we can determine or we can predict the next instance of the time. So how the signal will vary. So what the signal comes. Okay, these periodic signals are infinite signals. So they go on, they move on. Okay. So first thing we have to consider what a deterministic signal is. So the signal exhibiting no uncertainty with respect to its values at every instant of time or at any instant of time. You can call it anything. With respect to its value at any instant of time. Those are called as deterministic signals. And these deterministic signals are represented by a mathematical equation. Okay. So graphical example for this. So see, let us consider from this point to this point. You can take is a shape. Now again the same shape is repeating in the next one. Again the same shape will repeat. Again the same shape will repeat. So we can predict what will the next existence. So we can predict. Okay. Here there is no uncertainty. How the waveform is moving, I can know. That is, there is no uncertainty with respect to its value at any instant of time. Here I can know. Here I can know. Here I can know. Here. So at everywhere, at any instant of time, there is no uncertainty. There is no uncertainty with respect to its value at any instant of time. Hence, it is called as deterministic signals. Okay. So general, so cos signal, or we can go for sine signals also. Now, so graphical representation of deterministic and random signals. Graphical representation of deterministic and random signals. Let us go for deterministic signal. So first, my question is, so determine this one, whether this one is continuous time signal or discrete time signal. So on seeing this, we can simply say this is a continuous time signal. So I gave an example in the form of a continuous time signal for deterministic signal. Clear? Next. Okay. Next one, non-deterministic signals. Non-deterministic signals. So a signal characterized by uncertainty. In deterministic there is no uncertainty, but here we have uncertainty. A signal characterized by uncertainty with respect to its values at some instant of time. A signal characterized by uncertainty. A signal characterized by uncertainty. Very, very important. Uncertainty with respect to its value at some instant of time. Simple. At some instant, I doesn't predict what is the next value at some instant. At some point of instant, I doesn't know what exactly the pattern is. I doesn't know what exactly the value is at some instant of time. So those type of signals we call it as non-deterministic. So we can't determine the pattern at some instant of time. So we can't get the exact value of the signal at some instant of time. So it is varying randomly. Not properly, not a proper way. So those type of signals are called as non-deterministic signals. A signal characterized by uncertainty with respect to its value at some instant of time. At some instant of time is nothing but the non-deterministic signals. Simple. So we can't predict the next coming time instant existence. Okay, at the next time instant we can't predict what the exact pattern or what the exact value of that signal is. So those type of signals are nothing but non-deterministic signals. Simply we can say that a signal characterized by the uncertainty with respect to its value at some instant of time. Those signals are called as because simply they are varying randomly, hence they are called as random signals. So these signals are random in nature, hence they are called as random signals. Now, so we doesn't know what the next pattern is, how the signal is behaving. Can we define that signal with a mathematical equation? No, we cannot define that signal with a mathematical equation because we cannot predict the next existence of the signal with respect to the time. So how it is behaving, how it is moving, we can't predict that. There is no certainty, there is uncertainty. Hence we cannot represent those signals. With a mathematical equation. Simply, these non-deterministic signals are random in nature, hence they are called as random signals. So they will go for the classification like this: deterministic signals and random signals. So another name for non-deterministic signals is nothing but random signals. So random signals is another name for non-deterministic signals. So these non-deterministic signals are also called as random signals. They cannot be described or they cannot be represented by a mathematical equation. For example, see the below graph. So the below graph shows time on the x-axis and voltage on the y-axis, and the graph is like this. It is very random. It is unpeculiar. Okay, it is moving in its own way. So here a signal is behaving like one thing. So here signal is behaving one thing, another thing. It is moving randomly. Okay, so I can't predict what the next pattern of that signal is. So I cannot. There is uncertainty. There is uncertainty or no certainty. Uncertainty of with respect to the value at some instance of time, some instance of time. Hence, this signal is called as non-deterministic signal or random signal. So, the random signals, you can like this. Is a random signal. You can get random signals. So, it is moving, varying, or randomly. So, randomly, it is varying some randomly. This is the example. And clear? So, these are nothing but deterministic and non-deterministic. Now again, this signal is also a continuous time signal. So, I have given the two examples with respect to continuous time signal. Now I can give the graphical representation of this deterministic and non-deterministic signals with respect to discrete time signal also. Okay, that will be coming in the next slides. Okay, I hope you are clear with what is a deterministic signal and what is a non-deterministic signal. Okay, now the examples for the deterministic signals, cos, sine waves. So, and the examples for this one is, it is random. Simply, the noise generated in an electronic circuit, the noise signal can be treated as a random signal or non-deterministic signal. The best example is noise signal for this one. Okay, now a graphical representation of deterministic signal and random signal. Let us see. Here these signals are discrete. Okay, these signals are discrete signals. So previously I will explain the concepts of I explain the concepts of deterministic and non-deterministic signals with respect to the continuous time signals. Here I am showing the concepts of I am showing the concept of deterministic signal and non-deterministic, that is a random signal, with respect to the discrete time signals. With respect to the discrete time signals. Let us take this is the discrete value. This is the discrete value. Okay. So discretes. Let us consider these ones. I hope you are all clear. Discrete signals. Discrete signals, these are all. Now, here there is no uncertainty. There is no uncertainties of its value with respect to time instant. With respect to time instant, there is no uncertainty. So, this is the shape. Again, this is the shape. Again, this is the shape. Again, this is the shape. So, it is varying like this. Increasing, decreasing, further decreasing, increasing. So, there is no uncertainty. No uncertainty with respect to its value at any instant of time. Hence, it is nothing but deterministic signal. Now, see this one. See this one. Increase, increase, increase. Decrease, decrease, somewhat increase. Zero, increment, zero. So, see, there is a variations. Increment, decrement, variations. Same values, increment, a little increment, decrement, again increment, decrement, decrement. So, there is no proper shape. See, this is a proper shape, and it is repeating the same way. But there is no proper shape, and it is also not repeating every time. So, at each cycle, the signals are different. We have different signals. We have different values at different time instants. So, we can't predict. That is, there is uncertainty. There is a uncertainty. How the signal will be at this point, how the signal will be at this point, and how the signal will be at this point. So, there is no certainty. There is no certainty. There is uncertainty with respect to its value at some time instants. Hence, this is called as a random signal because it is varying randomly. Okay, hence it is called as random signal. So, I explained this is the graphical representation of deterministic signal and random signal by taking the discrete time signals as examples. Okay, because I said these continuous time signals and discrete time signals, continuous time signals and discrete time signals are classified into many ways. So, for the first classification is deterministic signal and random signal. So, in deterministic signal and random signal, I gave the graphical representation both with the help of continuous time signals and these discrete time signals. The same concept is explained with continuous time signals as well as discrete time signals. Okay. Now, next one. Let's say there is sinusoidal waveforms. So the best example for deterministic signals are sinusoidal waveforms, and the best example for random signal is a noise. The noise created in the electronic circuit, the noise signal is the best example. So we can't predict how the noise will be. So it's sometimes larger, it's sometimes so bigger, smaller. So it doesn't know how the noise will exist exactly. So the noise is the best example for the random signal, and the sinusoidal waveform is the best example for the deterministic signal. Okay. Next. So up to now, we discussed about two